Okay, I think we can get started at least with the some of the introductions here. First of all, I'd like to thank everybody, those of you who are taking the time to attend this webinar, and I hope you find it very interesting. This webinar is being hosted by Cerno Bioscience and being presented by Bob Strife at Procter & Gamble Retired. The webinar is titled Untargeted Small Molecule Formula ID using Orbitrap MS with Restricted Spectral Accuracy. Let me give you a little background on Bob. Bob was a senior scientist at Procter & Gamble for almost 35 years and has over 27, and that number may be off, I don't know for sure, but that's what I found out there, Bob, of peer-reviewed publications on mass spectrometry. He received a BS in chemistry from Rensselaer Polytechnic Institute and his PhD in medicinal chemistry and pharmacogenicity from Purdue University. Bob was a postdoc at the University of Colorado Health Sciences Center and a research fellow at the Mayo Clinic. And I say Bob is recently retired, and for many years he was one of the go-to guys for solving a lot of difficult problems using mass spectrometry at Procter & Gamble. And I think with that, why don't we start to kick it off here, Bob, and you can get started.
Okay, well, thank you, John, for the opportunity to speak today and for that kind introduction. And of course, the topic centers on determining elemental compositions of organic compounds, a task that I suppose most of our attendees have faced at one point or another in their careers. In particular, we're going to be talking about a relatively new tool that I have called restricted spectral accuracy. I also want to take a moment to thank our audience members for taking the time out of their busy schedules to listen to this presentation, and just give you fair warning that when you retire, you're actually busier than when you're working. So kind of works out that way. I don't know why. Now, while I have given many talks over my 40-something year career in mass spec, I have never given a talk to an audience I could not see. So in a recent conversation with a person who had been a webinar facilitator, I was advised that all of you are going to be multitasking this morning. And so they went on to advise me, you know, you have to keep them engaged. And I'm going to attempt to do that today with a mixture of some teaching, some historical anecdotes about the discovery of stable isotopes, a key concept that we're going to be using this morning, as well as discussing the technical results. And so I hope you'll find that blend to be engaging. The core of using restricted spectral accuracy really relies on the evaluation of ultra-high resolution isotope patterns that can be observed under the right conditions. And let me see if I can get our slides advancing. Here we go. And so the evaluation further relies on the Cerno Biosciences MassWorks software and a subprogram that's called self-calibrated line shape isotope profile searching. That's a mouthful, so we'll call it S-CLIPS. That's what it's generally recognized as. And again, the evaluation of these patterns is carried out by the software, and I call the patterns nature's fingerprints for revealing elemental compositions. Here's a brief overview of today's talk. We'll talk about the origin of isotope signatures in mass spectrometry and the fine structure that one can observe in isotope lines, and quote, because they're really profiles if you acquire your data in that fashion, and that's what you would do to carry out the kind of experiments I'll describe today. We'll talk on a brief historical perspective Who really discovered isotopes? It's a pretty interesting story, and it is filled with a little bit of controversy and a little bit of acrimony. Then we'll move on to the technical part of the talk. Why does the standard elemental composition determination drill, as I like to call it, why does it give a list of answers? And how can self-calibrated, well, let's say S-clips, okay, I'll stick with that. How does S-clips analysis of isotope-restricted data improve elemental composition determination to a single answer? It's pretty interesting. Well, where do isotopes come from? Now, you know, we've all had Chemistry 101, some of us longer ago than others, so very briefly, you all know that isotopes come from the result of adding extra neutrons to the nucleus of an atom, thereby increasing an element's molecular weight, but not changing its periodic table position, and that's where the word isotope comes from. It's from the Greek isotopos, meaning same place. Now, you're all well familiar with carbon-12, and if you add a neutron to the nucleus of carbon-12, you get carbon-13 with the same number of protons, same position in the periodic table. But the mass difference is 1.003355 daltons. And by the way, that is not the mass of a neutron. Considering boron-10, doing the same manipulation, you find a mass difference of 0.996367. And that is not the mass of a neutron. And the reason this occurs, of course, has to do with nuclear binding energies. And just as electrons orbiting the nucleus have preferred configurations, so do the nucleons. And this shows up, if you go to a table of binding energies, as every nucleus having a unique binding energy, and that means a different amount of mass to energy conversion, and that results in these mass differences. What it means is if I take the major monoisotope peak of a molecule and go to what is called the A+1 position, well, that A+1 position, depending on the constituents in your molecule, is actually going to have a fine line structure because each of those atoms has a different nuclear binding energy and causes a different mass shift. Well, here's a little Reader's Digest, as I call it, history of the discovery of isotopes. If you go back to the early 19th century, there were two fellows, Prout and Meinecke, and regarding the known elements of that time, they suggested that these could be explained as multiples of hydrogen, the lightest substance that was known. And this actually became known as the whole number rule. And so it was thought that hydrogen is a primordial particle. All the other elements are built up simply by glomming hydrogens together, and the elements are pure and stable. Adding further support to this was Mendeleev's famous work to develop the periodic table, classifying the known elements of the time into rows and columns of similar materials. So within a column, you had similar chemical properties, and then as you ventured across in the row, the properties would change. But this classification just added fuel to the fire that substances are pure and stable. Well, then the apple cart, as we call it, tends to get turned over at the end of the 19th century and moving into the 20th century. Thomson had discovered the electron, and its associated mass is 1/1800th of that of a proton, suggesting, in his words, that this corpuscle, if you will, was of a more fundamental primordial nature and needed to therefore reconsider what atoms were constructed of. Again, another real breakthrough was at the end of the 1890s by Becquerel and Rankine and Madame Curie on the discovery of radioactivity. And so now we had forms of substances that seem to emit mysterious rays, and Becquerel actually classified these as the alpha, beta, and gamma rays. And in particular, regarding the alpha rays, these soon were figured out as actually helium +2 being ejected from the core of the nucleus. So this really turns over all the early ideas in the 18th or in the early 19th century. So Rutherford then showed through his scattering experiments, of course, that the positive charge was almost a point charge, that atoms were largely composed of space, and that the electrons were likely in clouds around this positively charged core. And that turned over Thomson's idea of the so-called plum pudding model of electrons and protons kind of being mixed together. Well, the first real piece of physical evidence for the existence of isotopes came in a physicist's experiment. J.J. Thomson, and the parabola mass spectrograph that he built was really the first true mass spectrometer. And further than that, from the other field, from the chemistry field, we had Richards and Soddy and Hyman in 1914. And in an interesting experiment involving cleveite, which is an ore that is enriched in uranium, versus thorite, which is an ore enriched in thorium, they isolated the stable end product of multiple decompositions, that being lead. And the problem was the two different leads had two different molecular weights, and yet they were identical in every other aspect. And that, of course, is due to the fact that there's an extra neutrons in the lead isotope nuclei. If you want to read a little bit about this, there's a reference from Mass Spectrometry Reviews. I'll give you a second to jot that down. And this is where I gleaned a lot of this information I'm sharing this morning. And I'll have some other references for you later. So there is a picture of Thomson's real data. And the operating equations of his mass spectrometer are shown in the top of the slide. We're not going to get into that detail. But be aware that the atoms that are ionized are then focused in these curvy parabolas. And down in the lower right-hand corner, we see two parabolas. These are for neon 20 and neon 22. So this is direct physical evidence of the existence of isotopes. And in fact, in 1910, another fellow named Watson had determined the molecular weight of neon, and he stated, hey, this violates the whole number rule. Its molecular weight is 20.2. It's not 20. And of course, that's because he was measuring the average of that blend of neon and neon 22. So it all fits together very neatly. Of historical entrance, by the way, there's another reference for you. Give you a second to write that down. It's from International Journal of Mass Spectrometry. Now on the chemistry side, especially with the radiochemists, you begin to find what I call this acrimony, or who really discovered isotopes. And they had some very strong feelings about it. In fact, in his 1921 Nobel Prize lecture, Frederick Soddy stated, I think I may best fulfill my duty as a Nobel laureate if I try to disengage the real origins of the conception of isotopes. This task of tracing the birth of an idea is both difficult and complicated. Further, he went on to say, this year, 1907, marks the first definitive statement of the doctrine of the complete chemical non-separability of what are now called isotopes. Now, it's interesting to me that he was citing the work of McCoy and others and work that he had performed who failed to chemically separate thorium and radiothorium. Well, that's a negative outcome. I myself kind of look at negative experimental evidence. You have to be careful how you interpret it. I don't think that they really proved anything by the fact that they failed to separate them. Now, of course, their speculation was right, but it was really not until 1914 where they had a positive proof experiment, that being what I talked about regarding lead, derived from thorite or derived from cleveite. And so you have a negative result, then you have a positive result between 1907 and 1914. You have J.J. Thomson's positive result in 1912. Who really discovered isotopes, radiochemists or physicists? And of course the answer is they all contributed. They all contributed to this. Yet Soddy hung on to his claim as late as 1923, saying one of the most important consequences of the study of chemistry of the products of radioactive change has been the discovery of isotopes. Here's where you find something a little bit humorous. He says it's one of the few fields in the vast borderland between physics and chemistry overrun of recent years by an advancing swarm of mathematicians and physicists. But the invaders have found the chemist already in possession of the land, as it were. I found that pretty interesting. So with that little bit of historical anecdote, which I hope has kept you engaged, we'll move now into the more technical part of the talk. By the way, J.J. Thomson was a physicist mathematician. I think that was a little bit of a swipe at him personally. So, restricted spectral accuracy for definitive elemental composition. I need to talk a little bit about my context. I work in what I call the land of unknown unknowns, and it's kind of like working in a desert, like this poor fellow looks like he's on the surface of Mars, maybe. I call it a dry and weary land because you don't get any help. You don't get help from databases, for instance, as you do with other types of work involving the identification of unknowns like metabolomics. I worked in industry, and I got problems whose answers were not in databases. For instance, a new fabric care agent and its synthetic impurities. It's a new entity. It's proprietary at this point in time. It probably hasn't even been patented. I'm the first one to get a look at these impurities. They're not going to be in a database. Or, in one case, I was given an oligomer from a supplier that P&G chemist had decided to tweak, adjust a little bit with some chemical treatments, and that resulted in a stray peak in a liquid chromatogram. And, of course, the safety people have to know what that is. And the answer is not in a database. And I think you get the drift of what I'm saying. Discoloration issues, good sample versus bad sample, not in a database. So that's my particular context. These one-off difficult problems where you're trying to solve an elemental composition and you're not going to do it by matching up to databases of mass spectral data or annotated with MSMS data. That's not the approach you're going to be using. So let's go to the standard drill for elemental composition. You all know that you start by determining the accurate mass of the unknown at an appropriate resolution. I want to stress that when you do formula searching, it's critically important to select the proper error window. You all are aware, if you've done work like this, that there are a number of parameters that you have to specify before you do your search, and one of these is the error window. And you need to determine this for your instrument on the day that the experiment is carried out. And thereby, you'll derive the sample estimate of the standard deviation of your instrument that day, and you'll be able to select the correct confidence limits regarding what probability do you want to gain that when you have your list, your answer is, in fact, on that list. And then you have to be generous on other parameters when you're dealing with what I call these unknown unknowns that are not in databases. For instance, one of the parameters you can specify is, well, how many rings and double bonds do you think are in the unknown entity? You might even have a piece of data like a photodiode array spectrum that lends some credence to putting some number limits on rings and double bonds. But what I'm talking about today is leaving everything, what I call, wide open. Just leave everything wide open. This is a pure math-based approach to determining the elemental composition. So you know that you always get an answer list, and the reason for this was really poked at by Kind and Fien many years ago. In the mass space from 0 to 500 Daltons, and only considering the 6 atoms that I show there are over 1.8 million formulae, and they are not evenly distributed. They have peaks and nadirs if you look at how they fall, which makes the density in that space even higher. Some have speculated that, if we get enough resolution in mass spectrometry, and if we get enough precision and enough accuracy, and those are two different issues, can we then get down to one answer? And especially noting the work of Alan Marshall's group in Fourier transform ion cyclotron resonance work, that is where they're trying to head, actually. But at this point in time, it seems that probably we aren't there. Will we get there? I don't know. Time will tell. So further work by Kind and Feen at UC Davis, again, they state, no, mass accuracy is insufficient. You want to use isotope information. And in their article in BMC Bioinformatics, they showed that it greatly reduces the number of candidates on a list. So, for instance, just considering the ratio of what we call the A+1 and the A+2 peaks, again, those would be from elements with 1 and 2 more neutrons, respectively, you can get a 95% reduction in the candidate list. But it's still a list. It's not a singular answer. So the question that I propose, using restricted spectral accuracy and the SCLIPS subprogram found in the MassWorks suite, is this a better way to use isotope information and get to a singular answer for a truly unknown unknown? Well, what kind of isotopes do we want to consider when we're talking about these patterns? This is a list of the more common ones. I'm not going to talk about obvious things like chlorine and bromine. These are simple. We've had the ability to count the number of chlorines and bromines for decades, actually. So that's not of particular interest. If you're doing GCMS work, you're certainly going to run into silicone. You can see 29 and 30 with roughly 4.6 and 3.1% relative composition to silicone 28. That's pretty useful. Selenium, I've actually run into. That one's really interesting. Take a look at the spread of isotopes you find there. And so it goes. But the more difficult cases lie in the yellow band on the slide. So we're talking about carbon-13, nitrogen-15, O17, and O18. You can see that the relative abundances of those are starting to get pretty low. So it's challenging to get the data that you need to get a proper evaluation of the isotope profile. Now, of course, many of you are probably using electrospray. It's a very common and popular mode of ionization these days. It has been for a number of years. There are cation clusters, and you're used to seeing these, of the organic molecule with a cation. Even the cations have useful isotope patterns, and I note particularly potassium, magnesium, calcium, and iron. You oftentimes can find adducts of your molecules with these nuclei, and if you look in the appropriate place, you're going to find isotope information, and that can be very useful. Okay, here's some experimental details to give you an idea for, is this really tough? How tough is it? I typically would work with dilute solutions of materials, 2 to 5 microgram per mil, typical. We like to introduce things by HPLC because it gives you a varying concentration versus time profile, and that kind of allows you to cherry pick the best data as you examine the profile and see which spectra have the highest quality. In my work, using an Orbitrap Elite with a 240,000 resolution at M/Z 400. But something really important, if you look at what the user manual tells you, it says when you're doing HPLC work and determining accurate masses, set your target, that is the number of ions trapped in the cell for analysis, at anywhere from 500,000 to 1 million. And that actually works for accurate mass determination, but it does not work for determining stable isotope patterns, and I'm going to show you that in a minute. I typically would have to reduce these target values by as much as 40 times to get good-looking data. Now, the MassWorks suite of software interfaces very nicely to many manufacturers' software. In my case, it's Excalibur 3.0. You export Spectrum directly to the Cerno MassWorks and access the SCLIP subprogram to evaluate your data. All right, so let's just briefly review where does this information come from and how does SCLIPs work. Mass spectra, as you know, are conveniently shown as bar charts, but again, these are not lines, they're not bars. Typically, that's the result of centroiding data, and you want to acquire your data in the profile mode. By definition, the monoisotope line is due to the sum of the elements of the most abundant species, the sum of their masses in the formula to get that monoisotope line. The heavy isotope lines generally lie to the right of this line. That's not 100% true, but for the purposes of today's discussion, that's mainly going to be the case. So not always true, but usually. So the bars have line shapes, they have profiles, and because they have profiles, they have associated equations that describe these profiles. And in the case of FTMS data, it is a Lorentz line shape. Most important, fine structure is visible in these A+1, A+2, and A+3 lines at ultra-high resolution. So here you go. This is alanine pentapeptide. This is theoretically what the data would look like at the specified resolution of 240,000 at the A+2 position. So 2 ticks, if you will, 2 Daltons roughly above the monoisotope peak. And that is the description of those lines. And again, because of differences in the nuclear binding energy, these various combinations occur at distinct places. And I say this is a little bit like a fingerprint. And if you want to read more about some of my earlier suggestions about how this was useful, you can find this in Characterization of Impurities and Degradants, Chapter 4, Orbitrap High-Resolution Applications. That's a chapter that I wrote for the generalist. So even if you're not, don't consider yourself a mass spec guru, but rather a mass spec user, I think you might find that, that chapter in that book to be of use. So the question with a fingerprint, first of all, is can you see it? You have to see the fingerprint. Can you fit it? That's the other thing. And, people that work in criminology, they have all these little tricks for visualizing the fingerprint. Well, I have a few tricks for visualizing these fingerprints that I'll share with you. And then, of course, there's the question of, in the case of a criminologist, they're going to go to a database. But in our case, we're going to go to SCLIPs and see if we can fit that fingerprint with some formula. Well, here's what happens when you have too many ions in your trap. This is the same pattern that I just showed you on the previous slide. That was theoretical data. This is actual data. And in the red trace, you can see what happens. Again, the reminder, the position here is a blow-up of the A+2 mass position. So we have a very small window, 10, 20 millidaltons of data that I'm showing you here. At an AGC target of 1 million, you don't see a fingerprint. You see a single peak. That's the red trace. Now, if you reduce that target, which again controls the number of ions that are allowed into the Orbitrap mass analyzer, you begin to see the emergence of that pattern. You can see the distinct split in the middle. And if you further reduce the target to 25,000, lo and behold, there's your fingerprint. This is a critical issue. And in fact, it was reported, this phenomena was reported back in 2012 by Gorshkov, Fornelli, and Seibin, and the reductions in AGC targets that I needed to use were fully consistent with what these previous workers had shown. So it's always nice when you fall upon something and go dig into the literature to find support for what you're observing. Now, if you're in the business of criminology and you're trying to convict, as it were, the correct criminal, what kind of isotope fingerprint do you want? Do you want more complexity or less complexity? Well, I'm going to suggest the more complexity, the better. It gives you more of the fingerprint to match against your database, or in my case, to evaluate with SCLIPs. Do you want more intensity or less intensity? Well, as I showed on the previous slide, you want intensity, but not too much. You can ruin the fingerprint in the case of Orbitrap work by having too many ions in the cell. So you need complexity, you need intensity, you have to have decent signal noise, but not too much. And what I'm suggesting is that this A+2 position, as we refer to it, is kind of a sweet spot. It's kind of the place to land for complexity and intensity, with the caveat that in trapping devices, the number of ions circulating is critical. So, spectral accuracy, a new way to apply it. Again, definitions, the A line is the monoisotope line. We're going to be focusing on the A+2 area as kind of the sweet spot for complexity and intensity. As combinations increase going to the right, that's why we're at A+2. A+1 doesn't really necessarily give you that much information. A+2, as I showed on a previous slide, involves multiple combinations of various atoms, and sometimes a pure atom like sulfur-34, but you get much more out of it. I'm not going to say that it's always A+2. It depends on what elements are present. You may find A+3 to be useful as well. But be aware, of course, that the signal is heading downhill pretty rapidly as we move to the right in the isotope profile. So I want to talk about then these fine isotope patterns in the context of what I call restricted spectral accuracy. So here is a brief description of how this S-CLIPS works. Now, every instrument produces a theoretical line shape, and in this case it's Lorentz for FT data. But these devices cannot be machined perfectly, and so the line shape that you observe on your particular instrument is not going to be perfectly Lorentz. And yet, knowing the basic equation, you can tweak it a little bit if you're a clever mathematician, and that's what's been done with the S-CLIPS software, to get the line equation for your particular instrument. Then, this calibrated line shape, raw data, from your data can then be applied against theoretical line shapes for various formulas. And those line shapes, the theoretical ones, can then be corrected to look as they would look on your instrument. And so now you've got theoretical answers shaped to the calibrated line shape of your instrument that can be overlaid on top of your pattern and compared. And this is an evaluation called spectral accuracy, and it goes on a scale of 0 to 100% with a perfect overlay and a perfect match scoring at 100%. Can we use this to get a definitive answer? Okay, well here we go. Here is a short section of the alanine pentapeptide spectrum that's been imported into the S-CLIPS environment. How much of this profile should I use in the matching? Should I use the full profile, 374, 375, 376, and match that against the hypotheticals? Well, the answer is no. The reason being that, first of all, the 374 is the monoisotope peak. It has no bumps and wiggles. It is monoisotopic, and this is why we use it for calibrating the line shape. It has a pure line shape. You don't need to use it for anything else beyond that. And because this is a little bit like adding together scalars times vectors, the 374 peak would pull or contribute to your answer score way too much and basically washes out the contributions from the smaller peaks. So use it for calibration, but that's it. And then you go on to consider maybe I should use 375 and 376. Well, 375, that's going to be due mainly to carbon-13. I'm not going to say it's never useful, but you basically want to try both and see which one gives you the most definitive result. So now we're going to show you some real evaluation. Monoisotope line, A+1, A+2, considering all the lines, 2 of the lines, and 1 of the lines at A+2. So this is a typical answer list that is cranked out by the S-CLIPS software. After you import the spectrum in, which takes only a few seconds, and click on a couple of things, these lists will generally be calculated within 30 seconds. Sometimes faster, depends on how many atoms you allow to be considered and such. But wide open, 30 seconds is not unusual, or less than 30 seconds. And you can see in this list where I've included everything, A plus 1, A plus 2, that I've got 9 answers greater than 90% spectral accuracy. The correct answer is in position number 3. What happens when I go to restriction? So now I'm going to move to only considering A plus 1 and A plus 2. Well, now I have a much shorter list. I have 4 candidates between 74% spectral accuracy and 88% spectral accuracy, and my answer has now risen to number 2. If I go a step further and say, I'm going to consider only A plus 2, what happens? I only get one viable answer, and it's the correct answer. It's for alanine pentapeptide. The second answer isn't even close. It's at 69% spectral accuracy versus 91. So this is really an astounding breakout. If this had truly been an unknown unknown, you would certainly have landed on the correct answer. Here is a view of the profiles that you can display using the S-Clip software. Now, of course, I've lifted them off of display screens and put them into a PowerPoint slide, but you can see the individual overlays on the software. I just wanted you to see all 3 of them together. And you can see the top trace is giving a 93% spectral accuracy score for the correct formula of alanine pentapeptide. Well, let's try another example. Here is the molecule quercetin. 15 carbons, 11 hydrogens, 7 oxygens. And don't try to read the list. I just want you to get a grip on the size of the yellow box. I now have 22 answers between 94% and 98% spectral accuracy when I consider the entire profile, A all the way through A plus 3 in this case. Curiously, it's only a carbon-hydrogen-oxygen composition. My answer is way up there at number 2. It's still not number 1. That's where I'd like it to be. And I wouldn't like it crowded out by so many other answers that are close by. Moving to restricted spectral accuracy, my list gets a lot shorter. Now I'm down to 7 answers between 92% and 95%. And my answer is at number 1 with about a 1.5% breakout from number 2. Well, that still makes me a little uncomfortable if this is truly an unknown unknown and I'm using a pure math approach to determining the elemental composition. So that's considering A plus 1 through A plus 3. If I skinny it down to A plus 2 to A plus 3, I only have 2 answers that are really viable. At 70 and 73, a 3% difference. 68% is getting a little bit out of what I consider the viable window. And these are from 2 answers here, a C11 compound versus a C15. And using that information, C11 versus C15, one can go on to ascertain which is correct because of the large difference of 4 percentage points on the relative abundance of C11 compound and a C15 compound. What I find interesting, now in the upper trace, we have the overlay of the actual data with the number 1 answer for quercetin, the correct answer. And in the lower trace, we have the overlay for the 11 carbon compound. And what I've highlighted is the peak in the ultra-high resolution pattern that is due to the presence of 2 carbon-13 atoms. That will get you to the A plus 2 position. Now, the abundance of that peak is due to a combinatorial formula, and it actually magnifies the difference in carbon-13. If you look at the lower answer, you're now going to elevate that peak by almost 50% to get to that overlay. And I find that to be kind of a useful thing, and could deserve some further investigation. But it really makes that pop out, so that if you had to choose between number 1 and number 2, just by looking at the profiles, you could do it with your eyeball. Something else that was kind of serendipity here, we're going to go back to the alanine pentapeptide. And I want to talk about counting oxygen atoms. Just by pure luck, it happened that alanine pentapeptide also had 15 carbons, but it only had 6 oxygens, and at the A+2 position, they show up as O18, okay? In the lower right trace, we see the line, the horizontal line, between 2-carbon-13 position versus the O18 position. There's no slope in it at all, and if you calculate this manually, just using combinatorial formulas, that's the way it should be. So the actual data is spot on. Now, if you go to the upper left, you see the quercetin, which has 7 oxygen 18s, but the same number of carbons. And look at the tilt in that line from the addition of a single oxygen atom. So my suggestion is that if you run a few compounds of different carbon to oxygen ratios, you can construct a calibration line and read these tilts if you want to count, literally count oxygen atoms. Here's a final example as we get close to wrapping up. This was a little bit of a test. Again, it came into my lab as an unknown, and it was a negative ion case. It lit up very nicely in negative ions, but its mass was at 583. Now, resolution decreases as I go up in mass from 400 by the square root of the factor of the ratio of the two masses. And what that means is you can tell that most of the applications I've shown you today are below mass 400, and that's because of the high resolution that's available there. If you're going to work at higher masses, you're going to need an Orbitrap with higher resolution or an FTICR. They're out there, they exist. This happens to be what I had access to in my lab. Well, we cracked the nut because actually it forms doubly charged ions, and you get nice signals down around mass 290, 291. And so the resolution is very good there. And so what I'm showing you, again, using restricted spectral accuracy in the A+2 line of doubly charged anions are the 3 top answers that the S-CLIPS software popped out, again, using restricted spectral accuracy. And there's the overlays, and the correct answer is at the left, and the other 2 answers lie to the right. Interesting point about answers number 2 and 3. If you're a mass spectrometrist, you'll get this. Those are radicals. And that's because when I'm doing searching, I don't specify if I want even electron or odd electron. Even though with electrospray data, you have a tendency to want to say even electron data. It's true, especially in negative ions, that if you're dealing with a fragment, you can see radical ions. So I tend to leave that alone, but I look at the list and I say, well, answer number 1 is the one that I think is correct. It has 91% spectral accuracy. The next 2 best answers are radical anions, and the 4th answer is over 10 points away, which again, from my experience, throws it out. So conclusions. First of all, the observation of fine isotope lines is only possible by reducing the number of ions observed. The A+2 position represents a somewhat ideal compromise for signal intensity and fingerprint complexity, although again, I'm not going to say A+3 is never useful. You have to look at the data that you have and make that decision. But by restricting spectral accuracy to include only the upper isotope lines, large scoring breakouts are obtained, and they easily differentiate the correct elemental composition answer. Last, the data are in contrast to the reported use of spectral accuracy in the literature, where generally full profiles are considered, and especially in the non-obvious cases that don't involve halides and nothing obvious like lots of sulfur. These reports generally show you lists of competing answers, and they don't get you to the exact answer. So using restricted spectral accuracy and S-clips is a new way to do this, and I really need to emphasize, I'm not saying this is the do-all and the end-all. There are lots of good tools that are useful in determining elemental compositions. This is just one more tool for your toolbox, but it works really well, and you should have it in your toolbox if you're doing unknown unknowns. So with that, I conclude and I'd be happy to entertain questions.
Okay, thanks a lot, Bob. That was great. I hope everybody got something out of that. I think it's really intriguing. If you have any questions, I'd appreciate it if you just typed it to the host, and I'll send it off to Bob, and he can answer it. And we have a question here. I'll send you a copy of that, Bob. And okay. The question is, do you use? You see that?
I'm in the chat. Okay, there you go.
So you can read that out back, I think.
Yeah, do you use the A to A+1 ratio to estimate the number of carbon atoms in the molecule? Again, this is one of the tools in determining elemental compositions. You take a look at that A+1 peak, and at ultra-high resolution, you can actually resolve the carbon-13 line from the nitrogen-15 line, and then you can look at the ratio of that line, particularly the part that's only due to carbon-13. So there's a little bit of a caveat here. If you look at the natural abundance of nitrogen-15, I think it comes in at 0.3%, and it can actually, in unresolved data, in other words, if your resolution is too low, maybe you're running a time-of-flight instrument at, say, 20,000 resolution, that nitrogen-15 line will be on top of the carbon-13 line. And I've had cases, no kidding, where I've had as many as 12 nitrogens in a molecule, and that is going to skew that line. It's going to have a significant contribution, which, unless you resolve it, will create difficulty in counting carbon. So be aware of that when you're working with an unknown unknown. You can't necessarily assume that the nitrogen number is low, and nitrogen-15 can mess you up if you're not careful. The answer to that, of course, is hopefully get yourself an Orbitrap with 240,000 resolution, and then you'll be able to estimate carbon pretty nicely.
Okay. I have another question, Bob. I just forwarded it to you. Actually, it's quite relevant to your answer.
Okay. Well, if you knew that, I don't know, I don't particularly know if it's an unknown unknown, how I would know that it only contains one nitrogen.
Well, you might want to read the question, or read the question back.
Would you use only A+1 if you knew that the unknown might contain one nitrogen? And so the only thing that I can tell you about the mass number is of course, the evenness or oddness of that number. That will tell you if you have an even or odd number of nitrogens, and it could be, in the case of an MH plus for an even molecular weight, 0, 2, 4, 6, etc. So I'm not quite sure what the questioner is getting at. I often don't know how many nitrogens are in the molecule, and but again, if you resolve the data, if you use 240,000 resolution and you're below mass 400, I'll say in the case of an Orbitrap Elite, you can resolve that nitrogen from the C13 line and safely use it. And I think what the user is getting at is kind of, at the very least, in unresolved data, you can get an upper limit on the carbon number. Even if nitrogen had 12 nitrogens and a 4% contribution to the A+1 peak, if you just called it carbon-13, it would give you an upper limit on the carbon number.
Okay. Thanks, Bob. Is there any additional questions that we have for Bob today? Okay, it looks like we're done then. And again, I appreciate everybody attending. We will post this video if you want to pass it on to your colleagues or review it again. And you can, if you want to talk directly to Bob, I'm sure he doesn't mind. You can contact us through our open email address, and I'll be happy to get you in touch with Bob to discuss any of these issues if you're interested. So with that, we'll just call that a wrap. And again, thanks a lot, Bob. That was a great presentation, and thanks everybody for attending. And I hope everybody got something out of somewhat of a very novel approach to a very difficult problem. Okay.
Thank you, Don. Thank you, Don, and thanks everyone for listening this morning.
Thank you. Bye-bye.